In doing this workshop, we mostly just wanted to introduce you folks to how we went about making this scanner and introduce you to the tools that we used, because we're not super experts at this. We're not engineers by any means, but we take a very do-it-yourself approach and kind of that maker culture approach, and we wanted to build a film scanner for a variety of reasons. Josh's interest, he has an MA in film preservation, and I'll talk about my own with my background in history and the research that I've done. A lot of this work, the code and the files for the 3D printed parts and things like that will be on GitHub. The link will be provided to the arcade folks, so you'll be able to find that later on if you want to build it on your own, okay? As mentioned, we are going to move back and forth because we wanted it to be sort of that do-it-yourself model. So we wanted to show you how you could do this at home when you go back and leave here today, how you could build your own. If there's students here working with Robert or Jim, this apparatus we're going to leave at Rutgers, so it'll be available presumably for some of you to use if anyone would like to take this on. With the advent of some of the tools that we're using and the accessibility of software programs and libraries, I really think, like I said, most of my research it's all history, but I can work on things like this and I can contribute to things like this. And as all of you could probably do way more cool things with it than I can. But I was hoping to introduce you to a few ideas to spark your imagination in working with it. So just a bit about my own work. I'm a historian, but I'm working on a dissertation project on the history of stage magic. So I'm really interested in the effects that magicians performed in the early 1900s in America. Some of these are effects and illusions that I can't see anymore. They're not performed anymore. They're not performed in the same way. But I have plans for these. I have descriptions of the apparatus used. And so my start in like this sort of digital humanities work was in remodeling some of these plans and making virtual forms of them and realizing them. And I started this just as the 3D printers were coming out. So you've heard a lot about 3D printers already this morning and at the conference. 3D printing is a big part of our work as well. To make the custom pieces, we're using a small 3D printer from the University of Rochester's lab. In London, we use a MakerBot Replicator 2 to print out the parts. But these are, once you get the 3D files, you can print the parts, you could change them around and customize them to your own. But I found 3D printing in my own work. Like I said, I can't see these illusions anymore, but if I'm reading about something that was, say, invisible to audiences, well, I'm curious, how invisible was it? Or under what circumstances was it invisible? So I was able to explore that a bit. And then, just as you heard about 3D printers, I had to build one to actually use one. That kind of informed some of my thinking and approach to other projects like this, like in handling the stepper motors and things like that. All of it kind of built out of that sort of approach. And I'm happy to talk about it. If anybody wants to talk about this sort of work a little later on, I'm happy to talk about any of it as well. But for this workshop, we wanted to focus on the film scanner and how it's using accessible tools from like maker culture. So we're using a Raspberry Pi. It's a computer about the size of a deck of cards. It has a fair bit of processing power. It won't match up to your MacBook, but it does all right. Runs maybe like 30 or 40 bucks. And then there are add-ons for it, like a camera module that's $18 to maybe $25. So it's all very low-cost materials that we're using and things that you could get at the hardware store and things like that to put it together. Josh, you know the scanning equipment for digitizing film would cost.
Yeah, so like professional grade motion picture film scanning equipment is usually, $30,000 to $100,000 to do like frame by frame 2K resolution scanning or higher. I think like the cheapest one that I've seen that does like isn't sprocket driven, and I'll kind of talk about that a little bit more when we get down there, is like $6,000. So we were able to make this for about $100. And the goal is just to make like the cheapest, most accessible scanner possible for artist-run centers and community archives that may have film collections, like motion picture film collections, and so they could actually digitize their stuff and make close to preservation quality scans, and also just for access to their materials to get them out there.
And again, from my background, myself and colleagues, we go to archives and we have limited time there. Nowadays, it's a lot of setting your camera up and snapping a bunch of pictures and then going back when you leave the institution and then reviewing what you've got and trying to make some sense of it after that. And if you scale that up, it becomes more and more problematic to deal with. And so some of the approaches that I've taken, I've tried to find ways to have computers look at those source images and then provide me with some details of it so I can sort of make sense of it. And you can go online and find blog posts where people have posted their workflows for how to set up your tripod and your camera and take all your images as efficiently as possible, or to batch process those images when you get back. So a project like this is kind of along those same sorts of lines, but it's with film material, and we're using 16 millimeter film today, but it could be adaptable to other sizes as well. We started out last year, we built one, and again, my interests were in microfilm, and we built a first version that we'll show you some parts of to scan microfilm and then attempt to OCR it and things like that, so that you could work with massive amounts, because there's just so much film available in the film format, but there are now such impressive computer tools to work with digital information. It'd be great to translate that over and start working with it and see what people can do with it. So following along with the sort of open source approach, we also look for tools. I'm a big fan of processing, the tools that are free to use or that are very accessible to use if you're not an expert in the domain of computing or programming. And I'm by no means an expert, and that's probably why I love processing. So processing was developed for artists and designers, and the rhetoric around it is you're kind of building code sketches, but I found it was a really easy way. There's a lot of visual tools and image analysis tools and image processing tools built right into it that you can quickly get into altering these images. So I use processing for a lot of prototyping, and I'll show you some examples of that in a minute. Another place to go to if you do some creative coding would be Open Frameworks, and there's add-ons for Open Frameworks that help you do the same sort of stuff. So once you get the concept of what's going on here, you could sort of create your own or tailor it with the platform that you feel most comfortable with. OpenCV is sort of at the core of a lot of what we're doing for the analysis of the images that we're capturing. So OpenCV is another, it's an open project of computer vision tools. So the CV is for computer vision. And basically very complex functions for doing computer vision analysis of images can be wrapped up in, it's like included in libraries. So they can be called upon in a program in a fairly direct or fairly simple manner, and then applied to your project. So like I said, I'll show one a little later on how to add it into processing. Open Frameworks has an add-on for OpenCV as well. And Josh, you used...
So initially we had written this stuff using the OpenCV C++ library, but I've since ported it over to Python just for, it's much easier to work with cross-platform, and I can bundle executables really easily and releases that way.
So this project, it's not the first of its kind that's been done. I think it might be the most affordable. We were inspired quite a bit by this project, the Kinograph from a few years ago. It was designed, I believe, out of the ITP program at NYU.
Yeah, NYU, yeah.
And it's a very well-engineered scanner. It was almost like too engineered for us. We didn't have that sort of rack and bracketing.
I mean, the half the cost of your scanning unit is the T-slot aluminum that doesn't really have any sort of bearing on how well you can actually scan something. In my opinion, it doesn't serve as great of a function as it does in other applications, like for desktop milling machines like CNCs, where you need more strength and sturdiness. So we cut back on a large amount of the hardware, and also this one uses a DSLR camera. So those can be pretty expensive too.
And I just want to point this out, though. Like I said, this isn't the first sort of project you're going to do this. And if you take this on yourself, there are other resources you can kind of go out to and look to for inspiration, or maybe some code or some hardware files, some 3D files, that sort of thing. Now I mentioned we did this at the University of Rochester a year ago, and we were just experimenting with microfilm and trying to image it and process it so that we could OCR it and get it machine readable, so you could run image or text analysis tools on the results. And this is just a sample of what we produced that weekend. We used OpenCV tools we first captured the images, but then we did some image stitching to put it back together. And we got pretty decent results just from that with the Raspberry Pi combo, the Raspberry camera, and some simple stitching algorithm. For this project, these are a couple examples of what we're working with. This was the very first sort of test just to see if the Raspberry Pi camera could hold up. So this is with no backlighting, and I don't know, Josh took it.
Yeah,
you're probably holding it. Or
I was
something.
holding the camera and the film because I hadn't actually built anything yet. So I was just kind of messing around with it, trying to see like where I should be positioning things. So this is at, I think this is at the sort of the raw resolution of the camera, which I can't remember exactly what it is. It's like 3,000 and something by 2,000 and something. But the resolution we're scanning at is 2K, so 2048 by 1080 pixels, which is pretty impressive for a $25 camera.
This didn't have a lot of stabilization included either.
Yeah,
So.
because I was just holding it.
And then once he had the rigging set up, it's kind of dark. You'll see it better on the TV screen in a minute once we move over there. But the results are pretty impressive. And it includes features like the audio track, and it also includes like you can visibly recognize the perforations in the film. We brought lots of film, so if you don't have experience with 16 millimeter film, when we move over here, we'll pass them around so you can see it. It's quite small, and the perforations are really small, but they are recognized. You can recognize them in the image that I was capturing. And this becomes later on for one of the tools that we'll try to work with to capture the individual frames rather than just a static image of the field of view. So this is just a very brief overview of what we're going to cover. As we mentioned at the beginning, we're going to switch over to this area. Feel free to ask questions at any time and stop us. We'll also leave some time at the end for you to ask questions.
We found that we were already like packing up so much stuff on our way here that we left the projectors back in Rochester, but Robert had a 16 millimeter projector in his office, so this is a 16 millimeter film projector. I passed some of that film around. A lot of people, like the sort of early scanners were known as telecines. And the way a lot of these work, there was like one called a film chain telecine, which was essentially a retrofitted projector that had a CCD camera on it. And then they would do something called a pull down to actually be able to replicate the frame rate of film in NTSC video. So there's kind of a community of people that hack projectors and will actually use like machine vision cameras to do film scanning. So they'll swap out the motor. Inside here is just a DC motor, and we're using stepper motors on the actual scanner. So with the stepper, you have a lot more precision, precise control. So yes.
Is that how some people get bootlegs?
Maybe back in the 70s. But yes, and then there were also a lot of people that had film printers at home, so they would actually do like, they would bootleg prints. They'd make prints from prints and then like process them in their basement. So that was a way that there was a lot of bootlegging being done. So I know it's really hard to see, but these projectors are all sprocket driven. So they've got little like toothed sprockets that help feed the film through. And there's a take-up reel that pulls it all through. So I used to work as a projectionist, and did some work on. I still kind of fix projectors in my spare time, but essentially, this needs to be rewound, but the film would just run through the projector. I'm not going to bother threading it, but because the projector doesn't actually work, but it just runs through all of these rollers and sprockets, and then just takes up over here. And then there's a little sound head here, and we showed you guys those pieces of film. You can see the soundtrack along the side. You can see it really well there. So that's what's called an optical soundtrack. And so there's just light running through that soundtrack on a photocell, and so the different modulations produce the different tones, sound. Yes?
How does film capture sound?
So there's a couple ways of doing it, and I don't know. Do you guys do some 16 millimeter production here? Or?
No, all digital.
Okay, so usually the way that it was done was that you'd have like a field recorder, and you'd use what's called a crystal sync camera. So a camera whose motor was like locked in at 24 frames a second. So you would actually, that's why you have that slate. Like people have the slate that actually closes, so you could actually like match up the audio track with the film. So what you would end up doing is recording it on like a magnetic tape, and then there's a machine to take that and actually produce the soundtrack, the Optimus
Switch to
soundtrack.
this one because it shows the waveform
Yeah.
a little bit better.
Yeah. And so then you print a separate soundtrack, and then you run, your print material with the soundtrack through a printer. And I used to work at a film processing lab, so did a lot of that type of work, printing optical soundtracks.
So if you've seen like sound visualized as like waves, it's basically the black track on the white background on the side there.
And so a lot of artists will actually draw on the soundtrack, and someone like Norman McLaren, who's a Canadian film artist who was around in the 50s and 60s, actually the 40s too, he would actually do these soundtrack manipulations and create his own music that way.
The timing is different though for the sound versus the visual
Yes,
frame.
so depending on the type of gauge that you're working with, the sound is actually occurring further ahead of the actual image that you're seeing. It's because the sound head's down here and the image is here. So you have to then, there's an offset between sound and image that you have to account for when you're printing.
I just wanted to mention that in case you're thinking of trying to experiment with it. That's one of the issues, and we don't address it here, but syncing those would be very
Yeah.
problematic.
Yeah, so that's where we would have to actually use a footage counter, and what you would normally do is take like a hole puncher and punch a hole in it, and then sync everything up on what's called a film synchronizer, so you can put multiple reels of film together and wind through them. But you would have to sync all that up, and so we could do that in software as long as you sync the stuff up here, and if you say name your frames properly, you can figure out pretty easily how to sync that sound up, I think. So sprocket driven is nice because it keeps everything in registration, but it doesn't work very well with shrunken film because you run a shrunken film through this projector and it's just going to destroy it. It's going to tear all the perforations out, and you're going to have a lot of problems. Or even worse, if you have film with damaged perforations, you can't run it through something like this. So archival scanners they use capstan drive. So they're essentially just using tension to kind of pull everything through. So they have a very sophisticated kind of roller capstan system, and you use your little wrench to focus the lens. So you can move the camera mount in and out, and also focus the lens with this little guy here. What else? I'm trying to think. I think that's it. I think that's pretty much.
The Raspberry Pi just operates off of like a 5-volt USB.
Yeah,
port. So the
Yep.
power supply is pretty small for the Raspberry Pi itself. Motors draw more current, so
yes.
they have a separate power supply.
Yeah, so when you're doing motion control sort of projects, you always want to power your sort of logic separate from your actual motors. And in terms of electronic, there's not really many other electronic components, just a couple of capacitors and resistors on there to kind of even things out. Yeah, so I think maybe what I'll do is I'll just show you guys. Do we even need to bother printing anything? I don't know. I mean, everybody's seen 3D printers. That's just old news. Nobody cares.
If you do want to see that.
Yes, we're using, so the operating system that we're using is Raspbian Jessie, which is the latest Raspberry Pi operating system, and so one thing that I'd like to do is also make the whole operating system image available with all the precompiled software on it.
Oh yeah, that'd be cool.
It'll be done at the end of the day today, probably. I can do that. Yeah, they didn't take very long because they're so small. So all we have is just the mount for the camera, the mount for the backlight, and then just the hubs for the cores. And then the light and the cores also have little holes in them for set screws. So we're gonna just publish all of the dimensions of the screws and stuff too, so you can pick that up pretty easily. And that's not, that's not a big deal. Like, you can always, if you're gonna be drilling this, you can drill different size holes and use different fasteners. So essentially, the way that we have the scanner working, and I've sped up the transport just so you can see it moving through, but it's actually really slow. Because the problem, I mean, we were running into issues where we were thinking, like, we need to be able to, because it's motion picture film, we need to be able to get every frame. So we had a couple of different ideas where we would set up some sort of tripwire to shine through the perforations and try to detect them that way. But definitely the most successful thing is just kind of moving the film along and doing a low-res capture, and then detecting the perforations. When you detect 2 perforations, you then save out the high-resolution 2K file. And because we can detect the perforations, luckily, we've got that. It's the frame line is generally in the center of those perforations, so we can kind of extend a bounding box out from the center point of those perforations and crop the frame out. And then you would go and you could use something like FFmpeg, which is a command line video encoding tool that's awesome, to then animate the sequences, the image sequences into a video file at the proper frame rate. So I'm working on some other modules for it. There's a library called OpenImageIO, which is maintained by a guy at Sony ImageWorks, and you can work with a lot of professional image formats. So formats that the $100,000 film scanners output to. So we're gonna make that software available too, and then something to just animate the frames as well. But there are some some design kind of flaws here and there that we want to work out. But it's an iterative process. So this is already much better than the first one.
What's your sense of how much the settings need to be changed for each film? Is it a sort of trial and error process for each film, or is there more of a optimal settings that works on most films? Or
yeah, there's definitely going to be a trial and error process for each film, just for focusing it, and also those edges on print film are clear, but on something like reversal, they're black. So you would just have to, we were just kind of pre-programming some settings, but I'd like to be able to make like a GUI interface where you can just kind of line a frame up and see if it detects the perforations, and then save some settings that way. I made another one and it wouldn't fit, so I just glued it in. But what I would like to do, the ideal situation would be to actually kind of shave out this bottom part and the top and just try to get as much just the frame as possible. So essentially this is just the program itself doesn't move through this quickly, it moves much slower, but this is just to give you a sense of the motion and what we're trying to do here. Okay, let me just close that for a second. So one of the problems too is if you don't tape your film down, usually you have to tape the film down to the core, because as you can see here, it just kind of slips. Or you need to slide it into one of the, they've got a little slot in there that you can slide it into. But the film just moves through like that. I've got it going now. And you can see how quickly that's going through there. So we're going a lot, but you can, it's pretty steady. Those skateboard wheels do a pretty good job of kind of maintaining that tension. and keeping it steady. And you can kind of see, you know, you can see it's almost animating. And you can see there's some areas where the perforations are just completely damaged or missing. Those are some tests that I made. I actually drew onto the film.
Since you're using skateboard wheels instead of these, do you think it would work with like?
Pardon me, sorry.
With,
Stop this.
The holes are so small, and again, the sides are clear. Looking into it more, I think a film does filter most IR light, but it's like
The emulsion
treated.
itself.
Yeah, the treated film,
Not
or
the
exposed film.
edges.
So the clear film wouldn't do any good to it. So we started to look for other options, and we took the computer vision approach. So this is again an image of that same film capture, but it's eroded and like binarized to emphasize those perforations. So instead, we're identifying them through computer vision, so that then we can find those as contours or features within the image, and then draw your frames out from the center of those.